Hey gang, welcome back to Inverted Pursuits Laboratory. And this week we're starting a new series I'm calling HPR Design Principles or High-Powered Rocketry Design Principles. And to start it off, we're going to go over cluster rocket designs. Now, going over cluster rocket designs came out of my recent launches of Viper at the Cloudbusters launch in October 2020. I had a lot of questions on how it was done, and so I wanted to go over that in a little more detail. So to start it off, what is a cluster? Cluster is a set of two or more motors on the bottom of a rocket. Here's an example on the left of a 3 cluster on the bottom of a rocket, and on the right is actually an example of a fairly modern, yet actually fairly old use of clusters. This is the bottom of the Soyuz, and the Soyuz use the cluster design in the same way that we have to use it in the high power rocketry world, by angling our outside motors in. They don't use thrust vector control like US rockets do, so they operate or choose to operate on the same principles that we do. So cluster core requires that the forward centering ring, or this one here, has a closer hole spacing than the aft centering ring. The other one down here, as you can see in this image. So we have one here where the holes are really close together, and then one where they're really far apart. You can see it even better on this 2-engine one, where they're closer together on the forward centering ring, and they're farther apart. I rephrase that. Sorry, they're closer together on the forward, and they're farther apart on the aft. It's not much, but it's noticeable, and that's all it needs to be. It just needs to be enough. The point of doing this is it helps mitigate the chance that one motor igniting late or not igniting at all will not cause the rocket to veer too severely off course. The chance of a motor not igniting at all having a lesser effect or having less effect is increased when you have more motors. If you only have 2, if one fails to ignite, I'm sorry, but you're going to spin around and flip through the air. It's just going to happen. But when you have 4, if one misses to ignite, you still have 3 pushing you in the generally right direction, that you have a higher chance of going up rather than flipping. Biggest things we have here in the design of it is a concept I like to call the center of thrust, or angling the motors or canting the motors towards the center of the rocket or towards a common point. Now on the left here we have an example where the 3 motors on the bottom of the rocket are just perfectly straight up and down, and these are 3 inline motors. And you can see the center of gravity here that I've got marked in red and black is just there, and we don't have a point where all of the thrust is acting through. So if one of these were to ignite late or not ignite at all, the rocket would actually veer around this point and would tumble off to one side or flip through the air. If you want an example of this, you can go check out my Alpha or IPR02 video where I discuss some of my early attempts at cluster where I did exactly this. It just doesn't work well. Now, if we look at the one on the right, we have angled motors on the outside, generating a point called the center of thrust, the point at which all of the thrust of our rocket is acting through. Now, this helps that if one motor ignites a little later, doesn't ignite at all, we still have a common point where all of the thrust is acting through. So yes, while it will begin to veer off course, it will not be veering as badly off course. And my favorite example of that is a pendulum. So we're going to jump to a video of me talking about a pendulum using a golf club real quick. So let's jump there.
Alright, so we're going to take a look at this in the simplest way possible to understand center of thrust. So I've got a golf club here that we're going to use as our example. And basically we have a mass that we're going to treat as our CG. And then I can adjust what I'm using as my center of thrust point by moving my hand, or basically a rotation point, on the shaft. So if we have a center of thrust, or the point where all of our thrust comes through, below our main CG, we end up with this inherent ability that if anything goes off center, the rocket just naturally will want to tip over. Even a little bit of thrust off one way, and next thing you know, your rocket's tumbling through the air. Same thing happens if you have no cant on your engines. But now, if we flip this upside down, and we're even thrusting from a point that's just above it, it doesn't want to. But if we go ahead and exaggerate this quite a bit, you notice that when we get left and right thrusts, all it's going to cause are CGs wanting to stay in the same location, but if one of the motors that's canted is burning more one side or the other, all it's going to do is cause our rocket to tip downrange, which will only have it go one way, so the rocket will just end up angling over and tipping downrange. If one happens to burn out before the other, it'll actually start to pitch back the other way, but usually this is when motors burn out within a half a second of each other. So
All right, so hopefully that made it clear to you what happens when the center of thrust is below the center of gravity. We always want to keep it in front of our center of gravity. So center of gravity, again, is this red and black point down here. And we want our center of thrust to be in front of that because, as I said, objects like to be pulled into space, not pushed into space. Unless you're using a thrust vector control on the bottom of your rocket, which is really hard when you get into large rockets, even small scale rockets. It's only been done by one guy, bps.space, that I know of, Joe Barnard, and he's messed with it a little bit, but it's way easier just to use a cluster with angled engines or canted engines towards a center of thrust. So thanks for watching, guys. I hope you enjoyed this video as we took a look at cluster rockets. Please stick around for further videos in this series. Next we have coming up will be a video over a tool I made called Powder Calc, helping you calculate how much powder you need for your dual deploy charges.